Welcome to the after-lunch session, and we will have Garrett talking about Scalable is awesome.
Yes, it is awesome. I mean, who does not think that? Nobody. Scalable is awesome. So this whole idea started off with me getting this question all the time, seeing this question all the time. Have you ever been in a design session and said, whoa, wait a second, will that scale? Either you asked it or you were asked that question by someone else. Have you ever seen on a mailing list, I'm doing such, this, that, but will it scale? Have you ever seen that? So I see this all the time. And what's interesting is that people, so I personally think this is a very difficult question to answer. We'll see how difficult it is. But people will pile on with like very specific answers to very, very general questions, and it always confuses me. I'm always sort of weighing in at some point. I can't resist, and this is what I do. So I come in and say, okay, I know you want it to scale, but your application doesn't exist yet. So let's not talk about scaling something that doesn't even exist in time and space. That seems a little premature. Why don't you build something first? So that's step one. Okay, now that you have something, you've built it, put it into production, run it, deploy it, get some experience with it. So now you have this thing that you built, and you're going to put it into production, and then you're going to observe it. Now when you observe it, you're going to see certain things. You're going to get data. You're going to be in the realm of physics. You'll collect statistics, and you can judge, is this performing the way it should? Then, problems you can fix. Now, nowhere in this is the word scalable. Really, the idea doesn't even exist in this, and this is generally the approach I take every single time, and the response is, every single time, this. Oh, thank you for not answering my question. I wanted to know how it was going to scale, and you kind of blew me off with this sort of pedantic, oh, build it, it doesn't exist. I'm not trying to be a jerk here. I'm trying to actually be thoughtful and help sort of you think about what's going on. Before you get into optimizing something, that thing probably should exist. But this is not a satisfying answer. It is never a satisfying answer. So it got me thinking, maybe I'm doing something wrong here. Maybe I'm taking the wrong approach. I'm kind of viewing this as a technical question. But what if it's not a technical question? What if it's more of a personal, emotional question? It's something that somebody wants. Wait a second, they're not really asking about scalability. I don't even know what that word means. What I think they want is something good. They want a sense that they're building something great, something amazing. Now this makes sense to me. Then I'm starting to internalize. This is actually a word that has no meaning whatsoever, but it's generally used when people want to use this word. Now, this is the one I'm going to propose. Now, this is a serious proposal. I want to change the vernacular. I want people to stop using the word scalable. I want you to start using the word awesome. Let's just try it out. But will it scale? This simple question. Will it scale? Let's replace that. But will it be awesome? Well, that's a really, really good question. No. MySQL will not be awesome. MySQL, nobody uses that. That's not awesome at all. So now we can start talking about really cool technology. We bring in new databases and distribute, key value things and distributed this, clusters, and we can talk about awesome things and have a lot of fun. Because really, it's more fun to talk about awesome than it is scalable. So this is the premise. Right? If we're going to use a word that has no meaning whatsoever, or basically what we mean is we just want to feel good about what we're doing, let's be honest and say, rather than using this sort of technical mumbo-jumbo, scalable, we really want to build awesome software. It's a lot more fun, it's more direct, it's more honest, and I believe it addresses the real issue. Now I'm going to spend this entire talk, or most of this talk, getting into this. You think this is a joke. I'm actually not joking. There's a material impact on society because of this misconception that we're building something awesome, but under the auspices of technical engineering. So I want to kind of dispel that myth. Okay, so I'm going to break this down as follows. I think there's a myth of scalability. I think we use the word scalable way too often. I don't think we should use it at all, as I've said. So I want to try to establish that. I want to get into why I think we do this, because I think when we understand ourselves, our psychology, it'll help us to use the right terminology. It'll help us to get a perception of a good understanding of what we're doing. And then probably most importantly, I want to go through some patterns that I think I would apply in the realm of scalability. So when we're talking about scalability, we're often talking about accommodating changes in load of some type of change, some type of delta, usually an upward delta. So something changes and we want to accommodate that. I want to put some patterns out there, but none of the patterns have anything to do with scalability traditionally. So I'm going to call them anti-patterns. But I think if we use them, we'll end up building software that is actually awesome. It's really, really good. And we can actually measure it and we can prove it. And the word scalability just falls out. And instead we can just have fun. Okay, does that make sense? That's the game plan. So let's talk about the myth of scalability. Now, let me be clear here. I think that you can define scalability precisely enough that you can talk about it. But I believe in general, maybe not in general, often, people are talking about scalability in a magical sense, in the sense of infinite scalability. Will this architecture scale? That word, will this architecture scale, is not sufficiently precise to be an actual question. It means, will this architecture be good, or will it be great? Nothing scales infinitely, and I'll just prove that. There's this thing called an outage. It means your software is not working, it fell over. You can also have outages that are service level outages, where your latencies are too high, your service levels are falling over. So your application is technically working, but it's unacceptable. Those are outages as well. Outages happen all the time to everybody. Everybody. The most scalable, web scale, crazy, awesome companies in the world have had material problems with their architecture. Every single one of them. Twitter's been doing pretty well for a while now. But you can go back and read the amazing history of the transformation of their architecture. Somehow they powered through it, but there's no infinite property of scalability where you put something in place and off it goes. The process that Twitter went through was very much what I described before. They built it in Ruby on Rails. Come on. And Ruby on Rails has got this bad rap for being something that doesn't scale. Well, Twitter came back and said, you know what, that's actually not the problem there. The problem was architectural. But they built it, they deployed it, they observed it, and they fixed the problems, and they pushed forward, and they have an application that works. Is it scalable? It seems to scale, it seems to accommodate. I don't know how much they're changing. It seems to work pretty well, I know that. But there is no magical property of scalability there. Same with Amazon. I mean, the great Amazon. How many people here have been affected by an Amazon AWS outage, one way or the other? Yeah. CloudBees ran their platform as a service on this. I know intimately every outage that has happened over the last 6 years, intimately. I was there. There's just simply no such thing as an infinite scalable system. eBay, you can go on and on and on. Any one of these companies have had issues. So this is what I'm saying. Don't use the word scalable. There are more precise terms to use. I want to get into some of that stuff. So if you doubt any of this, go online and read. Every company goes through specific issues in time and space involving physics. And it's words like latency, throughput, response time, concurrency, or concurrent connections, very specific things that mean specific things. The term scalable is hand-wavy, okay? It's going to be something different. We want to use a different word now. All right, so nothing scales, so let's not use that word. I think we should use the word awesome, but if we're a little bored with that because it's fun and we laugh and we think, yes, we're going to build awesome software, then what? What's actually useful and productive here? I'm going to propose a word that has very, very little sex appeal, but I think is a very good word. If we really want to build good software, I think we should be using this word. This is the word. We should be considering suitability. What do we need to do? And understand that very precisely and then go do that. That's an engineering discipline. That is not in the realm of awesome. That is not in the realm of let's feel great about what we're doing, unless you feel great. I feel great about this. But it's not building magic. It's not building something out there that's amazing and cool. I believe you can get amazing, cool things with this, and we'll take a look at how that can happen. So, speaking of amazing, cool, this guy, fastest land animal on Earth, the cheetah. We love this guy. This guy is fast, is amazing, it's great to watch, pushes the boundaries of physics. I mean, the architecture of this animal starts to top off the meter. You can't really go faster with this particular design. But the reason the cheetah is fast is not because the cheetah wants to be awesome. The cheetah knows it's awesome. He's comfortable with that. He's cool. But he doesn't, he's not aspiring to be the cool kid. He's fast because these guys are fast. Antelopes are fast. And the antelope and the cheetah got into an arms race in an evolutionary sense. One gets a little faster, the other has to match. Otherwise, it doesn't exist. We wouldn't be talking about either of these if one had overwhelmed the other. And probably they both would have gone extinct. This arms race is sort of has an equilibrium to it as it goes up. But it's suitability that's driving this particular characteristic of the cheetah, speed. Now, this is a very fast food. This is a very slow food, right? So if your food source isn't an antelope, but it's a blackberry, right, you don't have to be fast at all. In fact, if you want to compare the relative fastness of predator to prey, the turtle is literally infinitely faster than the cheetah. That's fast, profoundly fast. Of course, the turtle is subject to predation, right? It's slow, so other creatures can come by and gobble it up. So what's its feature? What's its secret sauce? Huh? What do you think? It's the shell. That's right. So you have stuff like this going on. This is an actual event. This is not photoshopped here. This is an alligator who's trying to make a meal of this guy. And note the arrogance of usually a turtle would just like retract. I would retract. I'd be like, I'm not going anywhere near those fangs. But this guy's like, whatever, this is great. He's just hanging out. And what happened here, this is real, 15 minutes of this, and the alligator just gave up and left. So, we're talking about features that are necessary for survival. And I like to apply this to software. So the term suitable actually deals with precise things that we need to do. Joe Armstrong, you may have heard of him. There's this language out of Sweden, which is really cool. Said this: "There's no such thing as fast." And you'll see this. He'll pipe into these lists. If anyone asks about speed, Joe will say this every time, and it's great. We should all be saying this: no such thing as fast, only fast enough. And he should be saying it for another 25 and beyond. This is an axiom. This is something we should be living and breathing. I realize that I'm preaching perhaps to the choir here. But keep in mind, this is recorded, so others will see this. I'm going to propose some patterns that I hope will be challenging to you. I know that many of you are not obsessed with speed, but also I know that many of you did reply to that post on the list when somebody asked about, will this architecture scale? And you were proposing React Core, and you were proposing this thing and that thing and being very specific. And I'm just saying, maybe, don't do that, and just rephrase the question saying what you really want is awesome. If you have an actual problem, we're happy to discuss that. So we have this fixation on optimization, and you can kind of see it with the cheetah. You can kind of see it there. We like the cheetah. We like the cheetahs as fast. We're impressed by the fastest animal on Earth, and we have games that measure human optimization. How far can somebody throw the javelin? How far can somebody throw a shot put? A rock. Why is this an event? Well, of course it's an event because we're human. Right? We're programmed to capture and kill prey so that we can eat, and to escape prey. And so you have here the javelin. Here he is. You have the shot put guy up here. These are all part of our DNA. It's part of our programming. I mean, we are, by nature, directed toward speed, height, strength, agility. So our games measure that. And you think it's just going to, because we're engineers, it's going to stop at software? That psychology, that programming, that mandate to be faster, stronger, better is going right into our designs, right into our whiteboard discussions. You could be a little critical and say there might be some egos involved, but I prefer to say it's programming. It's the way we are built. I'm not even going to get into mate selection behavior here because that's a completely different topic, and but there's that, I think, possibly going on here. There's a lot of things that have nothing to do with software that drive our engineering decisions. So what I want to do here is sort of with this in mind, with our new self-awareness, we now are enlightened individuals, and we know that we wanted that distributed whatever because we're doing this for whatever reason. We can back off of that and say, okay, what are we actually doing here? What is necessary in this case to be suitable? Think of the turtle, not very fast, but cool in the jaws of that alligator. That's cool. That's awesome. So there's a consolation there. So what I want to do here is talk about some, I'm calling here antipatterns. So I'm not really even sure what an antipattern is. I like the name though, it sounds kind of revolutionary. But what I mean here by antipattern is none of these actually address scalability. But I believe they're important, and I believe that we should do them. And if we do them, we will be taking steps toward this goal of suitability. We'll be taking steps away from this concept of awesome. Let's be awesome. Don't get me wrong. When we're in those design sessions, let's have some fun. Let's dream. But let's at least be aware that when we talk about magic, and we talk about characteristics that we don't strictly need, we're engaged in that programming. That's fine. It's fine. Just be aware of it. Just be aware, and then laugh, and then move on to some interesting problems. Okay, so I'm going to summarize these, and I'm going to get into each one of them. So not a problem, build it naive, dependencies bad, think system, and physics, not magic. You were waiting for some actual substance. I think this is going to be substantive. And it takes us away from this, I think, silliness about fixation on these arbitrary characteristics of speed, strength, agility, etc. Okay. So every problem has at least one solution. Every problem has at least one solution. That one solution is this. You solve a problem by deeming the problem not a problem. There's a few snickers here. When I do that at work, there's always somebody laughing. Somebody always thinks I'm making a joke there. I'm not making a joke at all. Every problem needs to be vetted before you go solving it. And one of the ways you can solve a problem is to vet the problem and say, you know what? Not just to forcefully say it, but to, discover, verify, do we need to be doing this? Many of the problems with performance have to do with going out and solving problems that actually aren't problems. If you doubt that, look for it. Take a look, look to say, how many problems are being solved here that are just being generated by other things that we did? Like an ORM, for example, object relational mapping. Like, how does this thing, if there's no objects, right, there's no ORM. And ORMs are a bad idea in the first place, but if there's no objects, right, so we had, a sort of a non-solution. Maybe being a little hard on objects here, and I shouldn't be, but there's an example. There are things that come up in our design sessions that we can just deem not a problem and then move on to something that's interesting. What this does is it gives us the ability to focus on things that are actually important. And that process of vetting problems before we go blindly into solving them is incredibly important. I think it's actually more important than the solutions. Once you have a very well-defined, precise problem, the solutions tend to be self-evident and trivial. If you write functional programming, you experience that all the time. Okay. There's not a problem, and there's not a problem right now. Many people make the mistake of trying to solve problems that they think they might have down the road today. Push those off and focus on something that you need to do. Okay, build it naive. That's the next pattern here. So build it naive looks like this. I call it the unclever approach. Take obvious line of sight decisions. So don't be speculative. Don't imagine too much. Imagine a little bit. And this line of sight, this is something that's obvious to do. So you take existing tools, existing know-how, existing solutions, and you apply it as directly as you can. You will find that this usually works. It's line of sight, almost by definition. If it's obvious in line of sight, it should work. You're saying that it's going to work. So it usually works. And I found that it often works forever. These little unclever, not imaginative approaches you think are never, ever going to survive more than a few weeks, end up surviving forever. Because you misunderstood the problem. And we do that all the time. It's fine. It's not a judgment. It's not a bad thing. We just do. It's difficult to see in the future and know exactly what you have to solve. So when you build something with naivety, so I'm not going to be too clever with this, you give yourself the advantage, without spending a lot of money, to learn from experience and get to the actual problem. So that's anti-pattern number 2, build it naively. I see this not implemented a lot. People don't like this. It doesn't feel good to do something. It feels dirty. It's not the right way. There's somehow a morality associated with what we do. And being suitable just isn't good enough, right? It has to survive. It has to be, scalable. It has to be evolvable. It has to be this, that, and the other. Naive, direct approaches tend to get you into evolutionary position without over-speculation. All right. So if you doubt this, or if you need to make this argument, in a lot of cases this would be like, do we speculatively invest in some big thing? Do we bring Erlang into our organization? Nobody knows Erlang. Should we bring this in? Check this out. I think these things are, I'm going to give you 2 points and then a conclusion from that. See where we get. All right, this is a law. Cost of work is almost always underestimated. Right, so how many people are really great at estimating? We can be pretty good, but I always, 100% of the time, will underestimate the work. I just do. I don't make any pretense here. I'm not going to fake it. I'm just going to say I honestly believe it's going to take this long, and it always takes longer. So this is certainly in my case true. We also tend to overestimate the value. This is being optimistic. You optimize. You're optimistic on the cost, and you're optimistic on the value. So these two things work against efficiency in software development, and they make software development very expensive. Right? So one of the ways you can battle that is this build it naive approach, which is very simple. Keep work as small as possible and then improve incrementally. Because what you want is you want data to validate what your assumptions are, your optimistic projections. And the way you do that is drive the unit of work down to something as small as possible. So that is obvious, direct line of sight work. Nothing big, nothing speculative. So that's build it naive. Okay. Dependency is bad. Lately, I've been really railing against dependencies, and people are coming up to me and saying, "What's your deal with dependencies? Why do you hate them so much? You seem kind of fixated on this." I've been hurt badly by dependencies, and when you're hurt badly by things, you tend to not like them. I guess that's probably the most simple and direct and honest approach. I'll give you an example. So this was CloudBees. One morning, all of a sudden we got a lot of tickets. We had a lot of issues open. Literally every single application deployment. So this is a CloudBees platform as a service where we're hosting applications and providing a runtime environment. Literally every single application deployment was failing, 100% of them. There was no code change. There was no environmental change. All of our measurements and statistics and monitoring were fine. Nothing had changed. Literally nothing had changed. It's like, how on earth is this down? Well, it took a little while, not too long, but we tracked it down to an XML file. So every application had an XML descriptor of metadata associated with it. So this guy, you have to look in here, has this thing here. Now, I don't really get into the headspace of XML too much, so I step back from this. I don't want to get into that too deeply because I think it's a little disturbing. But it's got this thing called schema location. And what it's doing here is it's referencing an XSD file, which would, of course, provide the schema for this XML, and then you could use that to validate the XML. And lo and behold, we were using a validating parser who did look at this and said, oh, I'm going to go grab this thing. So guess what happened? A little server called java.sun.com was down for like a day. And it completely destroyed everything that we were doing. Wow, that's a really bad dependency. That's horrible. Well, we removed it by deleting that line. Not hard at all. Or you could turn off the validation on the parser. So that was an easy fix once we identified it. But this is an example of millions upon millions of examples where an innocent dependency can just tank your system. That's just one, very obvious one. You have dependencies that have interactions with one another. Dependencies tend to come with other dependencies when you bring libraries in or other software. So you're not bringing a dependency in, you're bringing in a tree of dependencies. And all of these things start to fall out of your control, and they start to erode the stability of your system. These are essentially moving parts. They're not literally moving, but they represent moving parts to your system, and we know about reliability. You want to drive moving parts out of a system to make it more reliable. Well, dependencies are moving parts, and they come with trees of more moving parts. They're very, very, very costly. So I have I guess you could call it a jihad. I want to fight dependencies. I want to eradicate them. You can't, of course, you eventually have to bring in something. I mean, if you don't have a language, if you don't have a computer, if you don't have power, there's certain dependencies that we concede. But for the most part, make do with what you have. Fight each dependency until it overwhelms you. There are cases where you have to bring something in, but just fight against it. Just realize that I don't want this thing. Right? This is now, it's like a pet. Right? It looks cute, we think it's going to be great, but then you get it and you realize this isn't working out, or this is a lot worse than I thought it was going to be. So fine, we all get pets at some point. We're always persuaded to get the pet. Great, I got the pet. But just minimize it and fight against it until you have absolutely no option. And then, when forced to, do it bitterly. I want like a grudge holding You keep your eye on that. I told you that was going to hurt us. I told you. So you either get your revenge that way, or you forget about it because it's fine. Either way. But have that grudge, that chip on your shoulder. Okay, well, this is an Erlang group, and I probably don't have to go into too much detail here, but think system. I like to talk about this because using the word system a lot is useful, especially, I mean, it's useful for ourselves, but it's very, very important when we're working with other people who are used to what I would describe as software environments that specialize in creating large hairballs or monolithic, applications. There are some that really specialize in that. They really want you to build an incredibly intertwined set of dependencies that called an application that share a common heap and are very, very difficult at a certain size to keep under control. Certain environments encourage that, and as a result, there are certain mindsets out there that are comfortable with monoliths, comfortable with large things that do lots and lots and lots of unrelated things, because it's one app. So a system is this. I like to call it independencies. So it's sort of the opposite of, basically what we're talking about are creating boundaries in time and space. So what I mean by time and space there is, it's not so much code abstractions, although there's a correspondence there. What I'm talking about are actual independent entities running in time and space. And that could be something like a core, a spindle, a network, a node, but it could also be a virtual machine, for example, that isolates processes, right? It's not physically separate. But there are guarantees made by the machine that create things in separate, independent, bounded areas. When you think this way, you tend to start to see things as follows. When you have a system view, and Erlang, I think, is probably unique in this respect because it is so system-oriented. It's called a system, right? When you start the VM, it's called a system init. The init subsystem within Erlang is modeled after the init scheme in an operating system. So you feel like you're booting an operating system when you run a VM. Your application starts to look like your app is actually made up of little apps, just like an operating system. So we're very used to thinking in terms of system here. The rest of the world is not. What you get when you think of systems is this. It's very easy to be focused. With these other points I'm making, be naive, build it directly, avoid dependencies. In a system view, you have the actual mechanism to do that. So I can just say, take an Erlang process as an example. I have a particular task. It needs to do this. It's one thing and one thing only, single-threaded, boom. I'm going to create a process that does that. We do that and live and breathe that. But so do sysadmins or DevOps people. That's what they call them today. Right? They do that all the time. It's a systems view. The more we can let systems view permeate our architectures, you will see the more evolvable, the more tooling we have, the less dependencies we have. We may have dependencies, but they tend to be isolated and independent. We manage dependencies. System view gives us all of this stuff. Is this controversial? I mean, come on. I mean, I know we all know this, but the cloud, right? I mean, the cloud, that's magic. It's part of our vernacular. It's part of what we do. We use cloud APIs. We use like HTTP and JSON all the time now. That's essentially magic. We don't know what's going on there. So, I mean, as much as this is sort of self-evident to us, it's where a lot of difficult so-called scalability issues go. We start to abandon our respective physics. So I have two quick points here. I can't cover all of physics in, I've got 10 minutes here, so I don't even know all of physics. I know very little bit, but I'm going to focus on a couple areas that I think would be helpful to get us out of the cloud, get our head out of the cloud. What I mean by that is get our head out of like abstractions that don't actually have measurable, tangible qualities to them the way we used to have that back in the day when we had computers and whatnot. Okay, so here's one thing that's interesting. This is a chart of latencies that it has a number of authors. It actually has accumulated over a period of time, and these are latencies measured in nanoseconds. And you start with a very, very fast operation, which is a level 1 cache reference of half a nanosecond, all the way down to 150 million nanoseconds to send a packet from California to Netherlands round trip. What's interesting about this is when you're talking about suitability, suitability is real. I mean, to do something again, in time and space for customers who are real and expect, millisecond latencies. You have to go solve difficult problems at times. And if you're not generally familiar with these qualities of physics, because this is physics here, something like this is helpful. It's helpful for me. Every now and then I should just look at this. Unfortunately, I don't have access to most of these things because we tend to run these in virtualized environments where these are all, it'd be interesting to see some of these performance numbers in virtualized environments. We can go buy an SSD, but we tend not to run those ourselves. And many of us used to, but I think most of us are running in cloud environments. So those take us away from physics. So an investment in understanding what's going on, and of course, when you're actually solving real problems, you have to get into these layers and measure things. So that goes without saying. I'm just talking about let's get reacquainted with what used to be sort of computer science. It certainly isn't going to hurt us. And I think what would be fun is if everyone were to have some of these things. There's a whole ecosystem of these little devices. They cost like anywhere from $20 to $50, maybe a little bit more. So you can buy them and just have fun with them. What's cool about these is they tend to be lower CPUs, lower clock rate CPUs. They tend to have unusual CPUs. We saw yesterday a coprocessor that was highly parallelized that could be exploited. They have GPUs. They have things that are existing in time and space, and they don't necessarily have to have anything to do with your day job. It's just fun. But it reacquaints us with electrons, which I think, as computer scientists, is quite fun. So buy these and then go build this. This is on display over here from Erlang Solutions, but these are Raspberry Pis and a Lego thing, and I don't know what it does, but it looks awesome. And we should just go build stuff like that. Why not, right? So this will reacquaint us with physics. It's fun. I've actually taken up soldering because I just feel like I repaired my phone. I took a microphone from one dead motherboard and I was like, well, I can't believe I just did that. It's like actual stuff. Okay, well, all right. So we have some time for questions, but I wanna just kind of get into like a preach mode here a little bit, and then I'll stop, and then we can open this up for some discussion. So we talked about this word. How many people will actually do this? I'm going to start calling it awesome. I just am. Why not? There's no harm in it. You're not being rude to people. Maybe a little bit. But I mean, there's good reason, I think. We'll see if it takes off. I don't know. Maybe it needs a video. I don't know. We'll see. We'll see if we can get this to take off. All right. So that's fun and that's funny and it's a little bit of a joke and it's a little bit serious, but really what is important here is this guy. So I would like us to reframe our thinking about what we need to build. And I know you do that, but I know you also don't do that. I know I don't do that. It's difficult at times because we want to jump into something that javelin, the shot put, the cheetah, all of these optimization fixations that we're programmed to do. But there's one word here that I haven't mentioned that underlies a lot of this, and I want to spend a little bit of time on that, and that's this word, evolvable. Part of the premise here, part of why I'm pushing back on scalable designs, scalable architectures, and it's not just because the word is completely meaningless and we shouldn't use it, instead we should use awesome, there's that. But the fact of the matter is that we can design as much as we want to. Physics is going to come and overwhelm something we didn't see. Right? And we have to be able to react to that. Otherwise, we're not going to exist. We'll cease to exist. This is evolution. Right? We have to adapt to evolutionary pressure. We have to adapt to the ecosystem. And it's just very, very hard to predict that. So when I see elaborate architectures, a lot of design effort going into something up front, I just get kind of nervous about it. Because I'm thinking, you're going to get all of this exactly right. You're going to have exactly the architecture that you dreamt of, that you feel great about. That's incredibly awesome. That's the best on the block. You can brag about to all your friends. But when you put that thing into production, I guarantee something is going to come by that you did not expect, and it's going to sideswipe you. That could be one thing. It could be 10 things. But it's going to happen. So knowing that, let's underinvest in our initial architecture and just get things going. But in order to do that, we have to bank on evolution. We have to bank on our ability to change and adapt to things that we didn't anticipate. So yes, that involves physics, and involves marshalling and harnessing and stewarding dependencies, so that our systems are as simple as they possibly can be. So when we come in to have to change something and evolve something and modify it, we can approach it with sense, with some common sense. We can approach it logically. It's just like functional programming. You spend time decomposing a program into, sort of symbolically what it is you mean to do. When you come back to try to make changes to that, it's very, very simple. You have a roadmap to make point changes based on the changed environment. That's true of functional programming, but it's also true of systems. I've seen this. If you have sort of a system of independent components that are small and focused, I mean, this is what? Microservices, this is SOA, whatever you want to call it. These are general principles of reality, right? You have stuff that can evolve, and that's the key to anything that's going to scale, right? It's evolution. If you look at the story of any of the big companies, one thing, this is something I spent some time with. One thing that's interesting, what comes out of it isn't an architecture. It's an internal culture around different practices in the organization. So an organization might say, we're just going to put this Ruby on Rails app out, and then we get crushed with demand that we never expected. And now we have to evolve. We've got to chip away at certain problems, and then realize, okay, to do that we need to get numbers. We need to measure. So you tend to see in organizations that have scaled architectures, they big, robust, tall, fast architectures. They tend to do a lot of measurement. They tend to be very scientific. They tend to know when something is starting to get slower and identify, okay, this is a problem. They can identify it 6 months before it happens. Because they can start to see, okay, this latency is starting to go up here. All right, well, let's take a look at that now and figure out what's going on. So measurement becomes a central part of these environments. But it's a process that they bet on, that their company, their organization, technical organization is committed to. So evolving, always vetting, you vet design decisions. Certainly you can get all of your experienced people in a room, talk about something before you build it. That's just as, I'm not suggesting you be random here. But what I am suggesting is that a scalable architecture is not a goal, right? We should be focused on getting something started and evolving it. And using some of these anti-patterns, I think, will contribute to ultimately so-called scaled architectures. But really what we're talking about is awesome software, because that's what we want. Okay, so with that, we have a few minutes for some discussion.
Hey there, my name is Thomas. Can you go back to the slide with the PIs?
With the what?
PIs, the raspberries.
The what?
Raspberry Pis.
Oh yeah, these. These or this one?
This one.
Okay.
Will this scale?
Well, let's do an exercise here, right? What's the objective here? We're going to change the word. Will it be awesome? I think it is awesome. Yes. Absolutely. It worked. It worked that time. So that's good so far. Yeah. 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 So the observation is the fitness standard, the survival of the fittest. So there's I'm using the word suitable. The observation is that this sort of evolutionary environment is survival of the fittest, and there is a fitness test. But there are also inefficiencies in nature. Nature doesn't arbitrarily optimize, so you could actually have an animal or an individual that's quite a bit more fit, quite a bit faster, but it's pointless and useless in the ecosystem. So that gets pruned back. There were probably some really fast turtles that that just didn't get to pass their genes on because it doesn't matter. And maybe the females aren't interested in fast turtles. I don't know. Yeah.
You talked about. You talked about picking simple solutions instead of over-engineering. That's a good approach, but it kind of requires the willingness to reconsider them later on and possibly scrap them when it turns out they were too simplistic. And you didn't mention that at all.
Well, I did use the word evolution, so that kind of covers everything. So yes, I did. No, you're right. So I didn't hit that, and I will hit that now. So when you take a naive decision, you're doing so with the expectation that that won't work at some point. I should have had that as a point, but that indeed is a point. When you make a decision like that, the reason it's naive, the reason it's the unclever approach is because you just don't think about it that much and you just go do it with the expectation that it probably at some point won't work. But if you have an evolutionary, evolvable system or system approach, that's really not a problem. In fact, that happens all the time. You go down a particular path, you experiment with it, and it works for a while, and then it stops working. But that's true of anything. That's certainly true of your elaborate architecture. It absolutely is. It just costs a lot less, and it will get you to the real problem quite a bit quicker than the elaborate architecture. Yeah?
Yeah, so this was about the fitness thing. Fitness isn't about being fit. It's just about being more successful. You don't have to be fast.
Yeah, we have to be successful in the right area. So yeah, so it's not actually survival of the fittest. I mean, this is sort of a misnomer. There's all sorts of inefficiencies that I mean, look at the peacock's feathers, for example. This has nothing to do with fitness for traditional survival purposes. It's a simple caprice of the peahen. The peahen likes these feathers. Why? Ask the peahen. You know, they got into an arms race where, you know, you'll see these things, bizarre, patterns in nature that have really, their liabilities. The peacock's feather is a liability to the peacock, but it gets the attention of the peahen. And of course, that's how he reproduces. That's how his genes move on. So I don't want to get into too much of that, but you know, so this is the mate selection programming that I was talking about. But in general, we want to optimize in the right area. Nature is very specific in channeling optimization as to what is required, not what is optimal. Optimal is like a moral judgment, and that doesn't exist in nature. All right. So I think we have one more question. We have time for one more question.
One last question.
One last question.
Okay.
Short answer.
Yeah. Hopefully this will be a short answer. More times than not, I get called in to re-architect somebody's system. They've grown it to a certain point. It no longer scales. Yep. And then everything has to be rethought. And so how would, you're in that situation, how would you approach using your thought, your thinking on this?
Yeah, okay. So I would bet some money that you're looking at a monolithic architecture there. I bet, almost every time. You're like, oh my goodness, what are we going to do here? Well, why would you say that? If it's an evolvable system and it's a system of small independent components, really your problem is going to be one in a few areas, and then it becomes fairly easy. You tweak these areas and improve these areas. But when you have a case where you're overwhelmed by the pathology of a system, that's a monolithic design. And I would just point to the dinosaurs. Now, the dinosaurs are an amazingly successful organism, species, over billions of years, obviously. But they went extinct at a certain point, and sometimes these systems just need to be shot in the head and redone. No, I'm serious.
I like that.
Okay.
Unfortunately, we have to stop there. So let's thank Garrett.
Thank you.